So, bem-vindos todos ao colóquio do Departamento de Física. Estamos recomeçando as atividades. É importante destacar que essa é uma das atividades nobres do departamento, a participação de todos é importante, muito bem-vinda, e, enfim, estudantes, por favor, participem sempre, façam perguntas, é uma coisa importante na nossa vida acadêmica. A palestra de hoje, nós convidamos o professor Claudio Conti, que o Anderson vai fazer a apresentação dele, e é um tema bastante interessante, conhecido de alguns de nós, e eu vou passar a palavra para o Anderson para fazer a apresentação do Claudio. Por favor, Anderson.
Grazie mille, Lúcio. Thank you very much. So it's a great pleasure to have Claudio here, even virtually, and hopefully very soon he'll be here presentially. I had the opportunity to meet Claudio in person. We had a workshop in India, which was fantastic in Mumbai. He's a very nice guy to interact with. Claudio, as far as I could gather, he got his PhD in 2002. I didn't know that. And he was undergrad in Fundación Hugo Borgonin from 1997 to 2001. Then he moved to the Universidad del Estudio Roma III, 2001 to 2004. Then he spent 2005 to 2007 in the Centro Fermi in Rome. And then since 2010, he's at Sapienza University in Rome. And 2011, 2013, he spent 2 years as a Humboldt fellow at the Max Planck Institute in Erlangen. So he works in many areas. If you go to his homepage, which I really recommend, particularly for the students, his homepage is starting by saying, just put Claudio Conti, it will appear this homepage. Read many books for many years and study things with one name like mathematics, physics, and philosophy. So I like that. He works in many fields. If you go there, he has a list with categories of things that he has been working on. And then this category links to the papers. It goes from biophysics, complex photonics, complexity, graphene, Ising machine. He's going to talk about this today. Machine learning, nonlinear optics, nonlinear photonics, option electromagnetic theory. So it's really everything based on photonics. And his work has been our inspiration, theoretical work back in 2006. And then his experimental work, which he's going to talk about in 2015. And then we kind of followed on his step with the group here, which is also very expert, Ernesto, Murilo, that groups that were formed by Mauricio. And then we have not yet collaborated. I have actually here André. André is one former postdoc of SID, and he's trying to. He was actually supposed to go to Italy, but the pandemic stopped at that time, and hopefully he can go back. So with that, Claudio, please, you have not the floor, but you have the airwaves. So all yours.
Thanks a lot of such so detailed presentation. I'm so pleased by your presentation. It's a bit exaggerated, so now I feel a lot of pressure. So, but it's okay. It's great to have to be in contact with you, and I hope that I can visit you in Brazil soon. And of course, looking forward to host many of you here in Rome. So it's now, as far as I understand, this colloquium is oriented also to students. So I will try to keep things very, very simple. And it's not easy to do that because the subject is actually complexity, and it is the most complex subject that I can imagine because it's about the theory of a complex system. So first of all, let me ask, can you hear me? Is everything okay with the microphone? Okay.
Everything's fine. Can hear you fine.
Good.
And the presentation is good. Okay.
So, thank you. So my name is Claudio Conti, and I am at the University of Sapienza in Rome. In the same university, in particular, the Department of Physics, there is also the Institute for Complex Systems. And most of the activity that I'm going to talk about is located here and is made by researchers working in this department and institute. More recently, we have a new institute in some sense because there is a new building, which is actually a very old building that now is ready again for hosting researchers. That is the research center Enrico Fermi. This was the original building where Enrico Fermi made his famous experiments more than 100 years ago. And now we are starting again a laboratory there. So it's also a very exciting place to work. So I hope you can have the opportunity to visit us soon or see this new building. And actually, I want to mention this because some of the activities I'm going to talk about are related to the work of Enrico Fermi, that is one famous scientist from Italy. He was a Nobel Prize. And also it is related to another Nobel Prize, an Italian scientist, who is Giorgio Parisi. You know, Giorgio Parisi is one of the winners of the Nobel Prize in Physics in 2021, so last year, together with Manabe and Hasselmann. And the talk today is related to the work of Giorgio Parisi in a not simple way, and I will try to explain this. And in particular, the subject, the motivation of the Nobel Prize is for the discovery of the interplay between disorder and fluctuations in physical systems from atomic and planetary scales. And I want to talk about a topic which is actually showing this interplay between disorder and fluctuations. And this is a very interdisciplinary topic. So in my talk, I will try to give many different things. And to explain to the students the basic ideas, I will keep a very shallow level, avoiding mathematical details, and then we can discuss if you want with the details. But I want to introduce a lot of many ideas, and in particular, I want to give you the main meaning of complexity in action in a specific physical system. And this physical system has to deal with photons. So the first question that we can argue if this interplay between disorder and fluctuation can be observed in photons. And the answer is yes. And it is also true that actually photons enabled the first demonstration or the most direct demonstration of the theory of Giorgio Parisi. So I will try to explain these aspects, and in particular, I will try to explain this interplay between disorder and fluctuation in the simplest way I can do that. So let us talk about fluctuations, and let us consider in particular lasers. So if you think to a laser, this is a very stable device that emits a very narrow line with, a light beam with a very specific color, which is stable in time. It is extremely stable. Probably the lasers are the most stable devices that we have. And indeed, we use lasers to detect gravitational waves, to make very sensible detectors. And so if you ask a question about fluctuations in lasers, what probably you can discover, you can understand, is that there is a specific law that is named the shallow Towns law, that in essence says that the more photons you have, the smaller is the fluctuations. So lasers are intrinsically stable device if you think to this situation. So you can think that there is no expected particular interesting behavior in concerning disorder and fluctuations in laser. But let us consider specifically what a laser is. A laser is a device that was invented more than 50 years ago, and it's a very simple device in practice. It is just two mirrors. This was the original design of a laser at its first invention by Good here. And it's just two mirrors and a tube that keep photons localized inside. And photons goes back and forth and they get amplified in time. And the first laser that was demonstrated was due by Theodore Maiman, and actually it is two mirrors with a tube. And inside of this tube, which is actually a crystal of some material, you have photons that are trapped and they get amplified. So a very simple device, there is no disorder, and you have a very stable emission with no fluctuation at all. But is this the only way that we can use to make a laser, to make the stimulated amplification of the number of photons? Actually, the answer is no. There is another way. And this other way was introduced also many years ago, more or less the same years in which the conventional laser were invented and developed by Vladimir Letokov, so 1966. And he proposed a different design for a laser. And the goal is always the same, just keep photons in a certain region of space and let their number amplify. And so you can do that by two mirrors, or you can do that by multiple mirrors, keeping photons bunching back and forth in all the directions. And this was named a stochastic resonator because it's actually a disordered system in which photons fluctuate and are localized in a certain region of space, and they get amplified. Well, it's quite interesting for me to observe that this idea is extremely related to the work of Enrico Fermi, because this is precisely the same design for a nuclear reactor that was also developed by Enrico Fermi, and also for a nuclear bomb in general. So in such a kind of device, you have neutrons that are scattered in all directions, they get amplified in number, and the very same situation is for photons here. So actually, this is an alternative design. I hope you see the mouse moving. This is an alternative device that is also able to provide a sort of laser action. But as you may understand, it's a completely disordered device at variance with the conventional laser. So this actually device was forgotten for many, many years, since the work of Anderson and Professor Gomez that is here, I have the pleasure to have in the audience. And they discovered this kind of a laser action many years after the first thinking by Vladimir, but actually Professor Anderson and co-author gave a very clear demonstration of this laser action. And since their work, the field of random lasers, as we know them, emerged and provided a lot of discoveries and interest in physics, and in particular, this is the subject of this talk. So random lasers are a specific device in which you have a lot of disorder, and so now we may ask, what about fluctuations? What is the situation for fluctuations in a random laser if compared with a conventional laser? Let me give you very, very interesting examples of experiments that you can do in random lasers. This is probably the most spectacular random laser that we did in the lab. And this is a granular material that we put under shaking by a mechanical device. So you can see these small spheres that are metallic spheres. They are put into vibration by some mechanical action, and at a certain point these spheres start flying, and they realize a sort of gas, a mechanical gas which is named a granular gas. And as you may see, at a certain instant these spheres are flying because of this mechanical energy. And so what we tried to do is to do a laser. In particular, we imagine that each of these spheres is a mirror. So you have a sort of an ensemble of flying mirror. And we ask if at a certain point they can form a cavity and emit light. And this is the real experiment that we did in the lab. I think you can hear the noise to understand the difference between a conventional laser. A conventional laser is a very stable and delicate device, and this is a very noisy stuff. So you can see these flying bits, flying spheres, and they form a cavity. And then we pump this system furnishing energy, and we retrieve the laser action by this system. So we try to realize in practice this multiple scattering medium, which is expected to localize photon and provide some kind of very disordered and stochastic cavity. And if we look at the laser emission of this device, you see that on average, you do not have any kind of laser action. So if you pump, you furnish energy, and you look at the emitted light from this device, here there is a picture. This is the pump laser, and these are the flying spheres. And you can see they emit a red light, and because they amplify red light because of a dye that is present in the system. And if you look at the emission in the red, it's typically absent, but at a certain instant, you have a very narrow line width that are emitted from this kind of system. So this is, I think, a spectacular example of what we mean for a random laser. That is a device completely disordered that, however, in certain specific situation can emit coherent light quite similar to a conventional laser. And of course, this is not the only way to do a random laser. And now I will give you other examples, but the principle is the same. We have disordered systems like this one. This disordered system in this case has very little piece of white material because there are particles that scatter light. So light is moving back and forth inside of this very small piece of material that also amplify the number of photons. And so you have photons that diffuse. And then you look at the emission from this system, and also this very small device that is more or less 100 micron is able to emit coherent light. So we see that from time to time, this kind of micron-sized lasers, which has some disorder, can emit sort of very narrow spike in frequency and hot spot in the emission. So this is another example of a disordered laser. And if you look at the spectrum that you can measure, you see many peaks. And these peaks changes from shot to shot. So each time that you furnish energy to the system and you retrieve this kind of laser light, you have a different shot, a different spectral content. So it is a sort of laser, but it has a lot of disorder, and it is extremely fluctuating. Each time that you turn on, you see a different thing. Each time you see a different spectral emission, you see a different direction and things like that. So a very complicated system. And I want to show you another example. This is a random laser made by a sort of ribbon. This ribbon is knotted and compacted in a very small device, which is tens of microns, like that. Also, in this case, you can use a conventional laser to pump, and you retrieve the emission, the spectral emission from this kind of device. And this is what you observe. These are some images from this device, and we turn on the device many times, and we see that from time to time we observe a spike here, or another spike here, or here. So we have something that it's quite similar to a conventional laser, but the spatial distribution of the light and also the spectral content changes a lot. So this is an initial introduction to give you an idea of the richness of this kind of physical system, which we now know as a random laser, and it has a lot of disorder, and it is quite noisy. So you can do the same thing. You can do stimulated emission with a conventional laser, and you do not have disorder, and you have a very stable emission. On the contrary, if you use a disordered laser, you have stimulated emission, but it is very noisy, and fluctuating. So there is a clear evidence that this is a very interesting physical system in which there is the interplays between disorder and fluctuations. But why disorder enhances fluctuations? Why there is this interplay? Well, this is actually the subject of Spinglass theory. Spinglass theory is the theory of Giorgio Parisi, the theory that is at the origin of the Nobel Prize of the last year. So in the following, what I want to talk about is precisely this theory. Of course, I will not talk about the theory with detail, with mathematical detail, because this is very technical, and I do not want to discuss this technical aspect, but just want to give you the physics. And in particular, I want to show you and to convince you that this theory has something to do with lasers. And then I want to discuss what a laser can do for such a theory. So how we can use this kind of system to verify the theory. And this verification is actually the measurement of a specific parameter that is named the Parisi overlap that you can do with random laser and you cannot do with anything else. So it is quite surprising that this photonic system enabled the direct proof, the direct evidence of some very advanced theoretical ideas that were invented in these spin glasses. And this will be the content of what follows. And of course, everything here is about fundamental ideas. So there is no applications. But now we know that there are applications indeed. And these applications are computing machines that are named Ising machines. And I think they are quite relevant for modern, also quantum computing. But I don't think I will have time to discuss this kind of topic. So eventually we can see after the talk, but I want to focus on these two aspects. So in particular to Spinglass theory and to the measurement of Parisi overlap. So what is Spinglass theory? Spinglass theory is a huge theory because it can describe a lot of things. It can describe, neuroscience, also DNA, but it is a theory that was introduced many years ago to describe anomalies in metals. So the response of particular materials to external excitation. But then it was applied to soft matter or to economy and social science, to string theory, and also to quantum chromodynamics. And it is also one of the fundamental theories of neural network and modern machine learning. It's a very powerful theoretical framework. And actually, I think it's the paradigm, the most important mathematical substrate for the science of complex systems. So if you want to study the science of complex systems, you have to start from Spinglass theory. And then you can do other things like, for example, networks or things like that. So, but what is a Spinglass? What is about this theory? Actually, it's in some sense is a simple story, because you just have a function. This function is typically the Hamiltonian of your system. And this function is a function of two different variables. One set of variables are the spins, and these are the relevant dynamical variables. They can be binary variables, or they can be complex, they can be vectors. And so many different kinds of systems can be, in some sense, identified with the system with spin variables. And then there are couplings. And the couplings, of course, couple the spins. And the problem in Spinglass theory is finding the minimum of this function. And this function can describe many, many different things, from string theory to soft matter, for example, and also random lasers. So the first, kind of theory of this type was introduced in 1920. So once again, more than 100 years ago. And by the work of Lenz under the supervision, by the work of Ising under the supervision of Lenz, and this is named the Ising model. And it's actually a very simple function of this way. where the spins are actually variables organized in a lattice here, like you can see. And these variables are binary variables in the simplest case, and they can be all equal to 1, for example, or all equal to -1, or also they can have some disordered configuration with +1 or -1. And the problem is indeed finding the minima of these functions, of this function here. And originally, Ising realized that there are only 2 possible states. And these 2 states can be described by a diagram of this kind. Actually, what happens is that if you have a lot of fluctuations, so if you have a very high temperature, all the spins are random and independently oscillate in time, and they correspond to a situation in which all the spins are independent. The average mean value of the spin, that is the magnetization, is 0, and that's it. So this is the simplest state that you can have, in which all the spins are independent. On the contrary, if you have no fluctuations or very small fluctuations, the spin can be either aligned or counter-aligned, so you can have 2 degenerate states with all the spin equal to 1 or all the spin equal to -1. So quite a simple situation, or complete disorder, fluctuations, or complete order. There are many, many physical systems that are described by this kind of thing. And this is a very famous video from YouTube, so forgive me if I'm not original, but this is quite interesting for us. If you consider an ensemble of independent oscillators like this one, for these are metronome, and they can vibrate independently from each other, and this is the completely disordered configuration, in which all the spins, in this case the spins are just this oscillator, for example the oscillator position or the phase, they are completely random. But if there is no noise in the system, and if we wait a lot, we will have this kind of phase. So at a certain point, we will observe that all these oscillators are in phase, which means that all the spins are just the phase of these oscillators are the same. And this is the ordered configuration. So this is a quite straightforward example that allows us to understand what is a completely disordered phase, like this one, and where the noise tells us that there is no order, or we have this other situation. I hope you can hear the noise, and I mean the sound.
It's
and so
perfect.
you see, when you have this kind of situation, you can hear that there is a periodical emission from this system, periodical emission of sound. Okay, what is the link of this kind of thing with lasers? What can we do this kind of things with a laser? Actually, we can do that. And if you are expert in laser physics, you know that there are specific lasers that can emit pulses. They can emit very short pulses. And these are typical conventional lasers like this one, in which you have many modes, many longitudinal modes. And these longitudinal modes have phases, and they can be in phase or they can be totally random. So all the longitudinal modes of this system can be can oscillate independently with different phases. And in this situation, you have a noisy emission, a noisy laser light from this kind of system. Well, this is precisely the same situation of independent oscillators. So once again, we can identify the spins with the mode phases. And once again, we can consider a situation in which all the modes are independent. And in this situation, we have a noisy emission from the laser. On the contrary, we can consider a situation in which all the modes have the same phase. All the modes are in phase. And in this case, you see that if you make some simple math, you realize that the laser can be a pulsed laser. So you can have periodical pulsed emission from such a laser, and this corresponds to the completely ordered case. So these are pulsed lasers, which are precisely the analog of this kind of system. When we have a disordered phase, you have a random light emission, and if you have an ordered case, you have pulses. And let me show a real example. This is a typical example of a pulsed laser system, and it's a commercial laser that probably some of you know in the lab of photonics or similar. And let me show you this video. This is an oscilloscope. This is the emission of the laser from in a situation in which you do not have this synchronous emission. So this is a laser with no phase locking and not synchronization. And when we realize the synchronization in such a kind of laser, we see the signal switches to a completely ordered situation in which you have pulses. So straightforward analog of a set of oscillator with laser systems. And I find this very, very fascinating, because at the end of the story, what I'm trying to say is that we take a simple model of statistical mechanics, and we can use such a model to describe very sophisticated laser systems in which you can observe a transition from a completely disordered laser emission like this one to a completely ordered situation in which you have a pulsed emission like this one. And all this story is described by the Ising model that was invented many years before the invention of a laser and the invention of the mod locking. The mod locking is precisely this mechanism that enables to obtain ultra short pulses from lasers, and the number of applications of ultra short pulses is huge. So it's quite fascinating that the number of applications of the Ising model include the applications of ultra short laser pulses. This transition is a transition that occurs when you have low noise in the system. So if you imagine the oscillators, you may expect that everything is stable, and if you are not shaking the table, because if you start shaking the table, you will realize that this oscillator will not synchronize. And particularly if you break the table and if you separate the oscillator, they will not synchronize. So to have a synchronization, you must have a low noise, as you can imagine. But the same is true if you increase energy. You understand that if the energy of this oscillator is high enough, they tend to synchronize. Otherwise, if they oscillate at a very low amplitude, synchronization is less effective, because actually they synchronize because of sound wave transmitted in the table that connect them. And if the energy of the oscillator is weak, they cannot synchronize. So this kind of synchronization occurs either lowering the noise or increasing the energy in the system. So all this story is to convince you of the link between the Ising model and laser physics. So far, without disorder. So far there is no disorder. And in particular, this is evident here, because as you may see, all the spin have the same coupling. So far, this is a theory that was actually, this connection is not very old. We realized that this connection just 20 years ago. And but the theory is actually very old. So this is the Ising model that, as I told you, is very old. But there is no disorder here. There is no disorder because there is just a single coefficient. So all the spins are connected by the same quantity, by the same value of the coupling. What happens if we introduce disorder in the system? Well, this is the spinglass. The spinglass is actually a system of spins that interact with random coefficients. And it is very important for many, many reasons. And it was originally investigated by Edwards and Anderson in 1975, by Sherrington and Kirkpatrick, and then by Parisi in 1979. This was introduced as a mathematical model with many, many interesting properties, and in particular for considering the effect of disorder, where disorder is represented by these coefficients that can be random or can vary from spin to spin. What the theory tells us about the effect of disorder? What is the effect of disorder in this kind of model? Well, the effect is very complicated, but the message is simple. The message is the following. If you have disorder, you have many, many different states. So at variance with a simple Ising model, in which you can have either order or fluctuations, you can have many, many different states, each corresponding to a different configuration of the spins. So this is named the energy landscape, meaning the fact that you have many possible states, more or less with the same energy. To make this idea concrete, let me show you once again another video. And in particular, I want to show you a situation in which we have a set of oscillators that are not equal. There is disorder because these oscillators are different. One is different from the other. So what happens when we put into oscillation a system of oscillators that are not equal? They are different. So let us see the dynamics of this system. And so we prepared the configuration of starting from the same position for all the oscillators. They start oscillating in a regular way, but after a while, we see that the way of oscillation changes. So there is this kind of situation which seems disorder. Then it passes through this other situation in which some of the white ball are synchronized, and so on and so forth. You can find that there is a lot of ways, of different ways, in which this oscillator move. And in time, you explore all these different states. For example, this is a state in which all the white spheres are aligned, and then all the others are aligned in this other way. And then we go on, and it continuously changes. So if we have disorder, we see that the oscillation is very rich because we have many, many different states that are explored by the system. And each time that we observe the system, we observe a different state. And even in this very simple example, you can identify a lot of states. So these are, say, 10 oscillators, more or less, and we have just seen a lot of different ways they can synchronize and they can oscillate. So this is used here to convince you that if you have a system of disordered oscillators, meaning a system with many interacting spins with different kind of properties, you can have many, many different states. And this is this is an evidence of the energetic landscape. So in this example, actually, any different energetically state that I've discussed here, shown here, correspond to a different collective mode of these oscillators. And in terms of Spinglass theory, this corresponds to a different configurations of the phase variables. So this is the main message about the disorder, that is the existence of a landscape like this one. Okay, this is quite interesting, quite nice, but it's not an easy story, because if you are observing this kind of system and you do not know anything about the system, you cannot say if this is a, say, fluctuating situation or if it is a competition between all these different states. I mean, in general, assume that you do not know that these particles are different. If you do not know anything, you see a very complicated and rich dynamics, but you cannot say if it is just noise, if it is just fluctuation, or if there is some structure, if there are many, many different states in the system. So what I'm trying to tell you is that if you have a complex system, you must have a way to distinguish complexity from randomness. So completely fluctuating system is apparently equivalent to a system that has many competing states. So can we distinguish these two things? Are we able to say that a system is complex or if a system is just noisy? This is a very profound and deep question, which is at the inner core, I mean, of the science of complexity. And so the problem is how we can describe such a kind of system and how can we say that we have many competing states? Actually, this question is the same if we say which is the order parameter of a spin glass. So the question is there some specific physical quantity that we can measure and that tells us that we are dealing with an energetic landscape? Well, this question, which is very complicated actually, is precisely the question that Giorgio Parisi considered many years ago. So what is the order parameter for a spin glass, for a system that has many states? And actually, to answer to this question, introduced the idea of the replica symmetry breaking. So in the last part of this talk, I will try to explain in very simple terms replica symmetry breaking. Replica symmetry breaking is one of the most sophisticated theoretical ideas that I met in the past in my career, and probably this is true in general. So it's not easy to explain these things in simple terms. So I will try to do that, and please forgive me if you are expert if I am oversimplifying. But I want to give this idea to some students that can be interested. So what is replica symmetry breaking? Replica symmetry breaking is a specific transition that we observe when we have complexity. In particular, you may consider two identical systems, and you observe the dynamics of these two identical systems, and you find that they are completely different. So you start from identical systems. They are complex systems, so they are disordered. They are formed by many different interacting parts. And then you observe, and you have two completely different situations. So two identical systems are different. So the symmetry of the two replica is broken in the evolution and in the dynamics. And this is due to the existence of many competing states, many modes, many collective modes on the system. How do we measure from a physical point of view this effect? We need to measure the Parisi overlap, which is the physical quantity that was introduced by Giorgio Parisi. What is the Parisi overlap? Let me try to explain. Consider two identical systems, and you make a measurement. So these systems are disordered, and you make a measurement. For example, you measure the position of this particle, and then you take another system and you make precisely the same measurement. If the two replica are symmetric, these two quantities are identical, and you can measure their product. So the product is just the overlap, the similarity of the two quantities. And if you get the same value, for example, the same value of the position of this particle, you have that these two quantities are equal to A. And then you measure the overlap, and you always find the same value. So if you have two identical systems and repeat always the same measurement, you obtain always the same value. So the probability of finding a certain value of the overlap is always the same. Now consider a situation in which the two replica gives different values. For example, you have this situation here and this situation here. In this case, you can have two values, say plus A and minus A here. And in this case, your overlap, so the correlation between the two measurements, can have just two values, so minus S squared and plus S squared. So you understand that when you have broken the symmetry of these things, this overlap distribution changes. So you always have the same value, or you can have different values. And you can repeat the argument, so you can have different states, and you can have different values of the measurement. And so the overlap will start displaying many different values. For example, minus A times B, or plus A times B. A and B are two different results of the measurement, and so on and so forth. So the probability distribution of the overlap changes from one simple shape to a complex shape. And if you repeat the argument for many, many replica, you arrive to the following conclusion. If you measure the probability distribution of the measurement, of the correlation of the measurement, you can have a situation in which you always have the same correlation. So this is the replica symmetric phase. So you measure this probability distribution and you obtain always the same peak. On the contrary, if you observe a different shape for such a distribution, which is a characteristic shape that I can explain with detail, if you measure such a transition, you can say that you have replica symmetry breaking. And you can say that your system is complex. So if your system always stay, in a fluctuating situation, the shape of this function does not change. On the contrary, if this changes, you have replica symmetry breaking and you have an energetic landscape. And this is precisely the prediction made by Parisi in his work many, many years ago, and actually calculated this overlap distribution in many different situations. But the fact is that this kind of transition was never measured. So no experiment were sufficiently appropriate to provide evidence of this replica symmetry breaking transition. So what we did is actually trying to measure this kind of transition and using lasers, using these very complex random lasers. So what we did is actually considering our very fluctuating laser system, we measured the spectrum, for example. So this is actually our observable, the quantity that we are able to measure. And we see that this spectra changes a lot from shot to shot. And we calculated the overlap. The overlap is just the correlation of one measurement with another. And so we make many measurements. Each measurement give a different quantity. So we may say 100 measurement. And so we can compute all the overlap between this measurement. So we have thousands of values of the overlap. And then we can compute the overlap distribution function. And we can do that by varying the energy in the system. And we found that a very low energy, this overlap has this shape. And if we increase the shape, the energy, we have progressively a transition to the shape that is predicted according to the models based on Spinglass theory. So in random lasers, there is a straightforward evidence of this transition, which is a thermodynamic transition. And actually, it's a transition to a regime that we call glassy mode locking. So I mentioned the mode locking as the transition described by the simple Ising model. This is a similar transition, but in a regime, in a situation in which you have many different synchronized states, precisely as in the case of the disordered oscillators that I've described before. So the existence of this transition and the evidence of this change in the shape of the overlap is what we need to say that we are dealing with an energetic landscape. What we need to say that random lasers are really complex system in the strict sense provided by the Spinglass theory and all the related developments. This measurement was then repeated by us in other random lasers to show that this is a sort of universal effect. This is the ribbon random laser that I've shown before. And again, we have evidence of this transition in the shape of an overlap. And also these experiments were done by your group this is also done in another experiment by us in for nonlinear system that I do not want to describe. But I want to mention in particular the experiment by Anderson and D'Araujo. I'm not sure I pronounced this name precisely. But I want to mention these experiments because they were beautiful experiments that also repeated and given much more evidence of this effect with very controlled physical system and random lasers. And so this kind of evidence of this replica symmetry breaking was reported by many different groups, and it is considered as the first direct measurement of the Parisi overlap, and in particular they were mentioned in the scientific background by the commission of the Nobel Prize. And so this is, I think, a very important result, because what is really impressing me is the fact that random lasers that are completely unrelated to spin glasses were able to demonstrate this kind of theoretical prediction. And this is also the beauty of the science of complex system that enables to link in such an interdisciplinary way all these fields. So I think I am arrived at the conclusion. I hope you are all online, because I do not see anybody. So I hope you are still there.
We are here.
Okay, thanks a lot. So let me just conclude with a simple, with some personal remark. That is the following. I have been talking about photonic spin glasses since 20 years ago, impressively enough. And I remember that people working photonics were totally, without words about these kind of things, because these kind of things are so far from photonics, from modern photonics, that is quite difficult to try to understand them. But I think this is a very nice example that we need to forget the borders of scientific disciplines, especially for young students and for researchers. Forget about borders. Statistical mechanics is not independent from laser physics, so try always to keep in mind that if you jump the borders, you can find a lot of very, very nice physics. And thanks a lot. This is our group, and thanks a lot once again. It has been a great pleasure for me to talk here with you. So I'm open to questions if you want. Yeah.
Thank you, Claudio, for a very, very enjoyable talk. I would like to ask the audience to open the microphones and give a round of applause to Claudio, please. Okay, so now we're open for questions. I see that there is already questions in the chat. Emmanuel, do you want to speak, to ask your question, or? Okay, somebody has a microphone open. Well, I'll read the question here. It says, the question is, can we say that we have replica symmetry breaking without calculating the overlap parameter, similar to the pendulum example? I don't understand the question, but
you can say that phenomenologically. You can see two things that they are identical and they behave a little bit different, but you cannot say that you have replica symmetry breaking, because you have to measure the states of the system. So it may happen that during the dynamics, the two replica are a little bit different, but they are not visiting different states. So it's measuring the Parisi overlap tells you that you are indeed visiting the different states. I hope this answered the question.
Okay, thank you very much. Claudio, I would like to make a slightly different direction, but from your previous work, I saw that you have an interesting paper on random lasers and mode locking. I work with mode lock lasers, so I'm always trying to find the connection. And there is no randomness, but in your experiment and your proposal, could you talk a little bit about this situation where you have a random laser and a saturable absorber?
Okay, very, very good question, and not an easy answer to this, because in random laser, you do not have a saturable absorber. So
Right.
you do not expect conventional mode locking. On the contrary, you can expect complex mode locking. So what you can see in a random lasers is the complex interaction may provide some sort of synchronization. So some part of the modes can synchronize, other part of the modes can synchronize at the different phase. So this gives you some sort of pulses emitted by the laser, but it's not the conventional mode locking. It's still a noisy situation. And I think that, I guess Anderson made some experiment with a fiber, if I remember, with many, many modes. But so you can have some sort of mode locking, but it's not a nice mode locking that you like.
Okay.
Yeah.
Okay, thank you very much. Anderson has a question.
Yeah, thank you very much. Very didactical talk. I mean, I think I now understood what's going on. You mentioned that you'd be talking, I know there was no time, but you have something recent on easy machines. Can you comment a little bit?
Oh yes, that is. But I need 2 or 3 minutes for that, because it's
no
not
problem.
quite.
I mean, I know it's time
Okay.
for your Friday wine,
Okay.
but just a few more minutes, and for us it's fine.
Okay, so I try
time.
to. Okay, I think you still see my slide, maybe. Do you see that?
Yes.
Okay, so all this story is very complicated, and but the problem is, can we do something with this stuff or not? Is this just fundamental physics or not? I have to admit that at the beginning, the answer was, okay, this is totally useless, but very, very interesting, so I want to do that. But now I think differently, because I understood that many important computing tasks actually maps to the finding the minimum of an Ising Hamiltonian. So, for example, this is named Combinatorial Optimization. If you consider you want to divide this cake into 2 parts, you can do this, or you can do this. So this is an example in which you have a computing task that has not a single solution. You can have a computing task that has many, many different solutions. And impressingly enough, and I skip the details, I can do another talk in another day if you want, but this maps to finding the minimum of an Ising Hamiltonian. So you can map different computing tasks to the minimum of an Ising Hamiltonian. If you are able to control the coupling coefficients, you can use your physical system to find this minimum. So the problem is the following: if we are able to build, say, random lasers in which the couplings are controllable, we can use these devices to solve a combinatorial optimization. And this is quite important, because in random laser, we can have millions or 10 of millions of modes, which means that we can solve combinatorial optimization at a scale with millions of variables that is inconceivable with conventional computer and with quantum computers. You know that quantum computer now can reach, say, 1,000 qubits to say, but really they are 100 qubits. But if we are able to do this with millions of laser modes, this probably will open many, many interesting directions for applications. So this is the main message. I can continue if you want to. Please let me know. Okay.
No, great. Thank you very much.
Fernando, por favor, please.
Thank you for your talk. Very interesting. Perhaps we have time for one last question. So you say that this is relevant because you can solve a computational problem with many more cores than a usual computer could do. My question is the problem is still non-polynomial in complexity when you use this kind of physical system to solve it? I mean, so are you changing the class of complexity, or you are just presenting a much more efficient way to solve it?
Oh, that is also a beautiful question. Okay, so let us start from this. We map the problem to finding the minimum of an Ising Hamiltonian. So we map the problem to J, the couplings. It turns out that for some J, your problem is class P. And for other J, your problem is class NP. So with the same machine, if you can control precisely the coupling, you can deal with the simple problem or computationally hard problem, both of them. So you can have both the situation. And so, but the problem is controlling the coupling. So we need to invent new machines that enables to control this coupling. I hope this is enough to answer, or I can say more.
Yeah, sure. Thank you.
Okay.
Thank you very much. We have time for one more question. Anybody? Well, if we don't have any more questions, I would like to thank the speaker again for a very, very pleasant talk. Thank you very, very much, Claudio.
Thanks a lot. It has been a great pleasure for me. Yes, thanks a lot.
Thank you very much, and have a nice weekend. Very nice seeing you.
Yeah.
Hope to see you soon.
It was
eventually.
Soon. I hope the same. So have a nice weekend. Okay.
Yeah.
Bye-bye.
Well, thank you very much. The talk was precisely the kind of talk that we needed to open our colloquium here. Okay.
Yes, you're too kind, but thanks a lot. Thanks a lot. I appreciate it. Yes.
Okay.
Bye-bye.
Bye-bye. Thank you, Claudio.